Hi, this is part 2 of the Power Up Display Counter project. I'll link part 1. If you haven't seen it, may not make much sense unless you, well, no, it's probably a decent standalone video if you're into like low power LCD solutions and stuff. So I won't recap that video, but just an update. Not a huge amount. Basically, no one really pointed out any alternative 7-segment e-ink, e-paper displays that were suitable. You know, there's a couple in here that we basically got down to, and we could potentially get those, but I tried to contact the manufacturers, haven't really heard back from them yet, so I don't know. I'm still looking for an e-paper, e-ink solution, and we may have to go for a graphic solution in that particular case. So anyway, that's still not off the table, but it did pretty much rule out in the previous video that 7-segment e-ink displays, while you can get them, they're not really a thing. They're all just graphic these days. So, you know, they're a pretty specialized thing if you want to actually get them. So what quite a few people asked for is that they wanted to know about the little Sharp memory LCD that I showed. This is an LCD, but it's manufactured by Sharp, and it's basically an ultra low power dot matrix LCD solution. Now, this is not a 7-segment display, it's dot matrix, but that's okay, we can work with that. So what I'm going to go through in this video is just looking at the options and some calculations on how long we can get an LCD solution like this Sharp memory one or a regular LCD to work from a rechargeable either supercap or one of those little surface mount rechargeable batteries that you can get these days. Because quite a few people said, oh, just get a regular microcontroller and just don't do an LCD and have a coin cell battery or whatever, and Bob's your uncle. Well, okay, well, let's have a look at that solution as well. So these are the Sharp memory LCDs. This is the one that I've actually got here. They're all dot matrix though. They're a 3-wire SPI interface, so you can drive them with a little 3-cent Paduk microcontroller. Hopefully I'm going to have a follow-up video with the Paduk microcontroller, actually getting one of those up and running with a do-it-yourself programmer and also an open tool C compiler. The one I've got is 29 by 6 millimeters, perfect, and it's 6 microwatts static power consumption and dynamic power consumption when you're changing stuff on the display, which we don't need to in this case. It's just a counter that just stays static playing, but 6 microwatts at 3 volts for this thing. That's only 2 microamps. There it is, 3 volt supply. That's 2 microamps. That's the sniff of an oily rag stuff. Now, of course, the downside to these is that they're not particularly cheap. We can get them in stock from DigiKey. Look at this, 2,700 in stock, no wuckers. But even in 1,000 of quantity, they're $8 US. We're just going to assume that cost is not really an issue here. Now, unfortunately, the data sheet is just a link to the brochure thing, which is like, it's nothing. It's got no technical details on there. I don't know, is it an NDA thing? You got to contact them, presumably. What's the protocol for driving this? Anyway, let's just assume that we can drive this thing, and it's 2 microamps supply current. That's what we have to beat with any alternative solution. Now, to give you an idea of how low 2 microamps is, let's have a look at a CR 2016 watch battery, for example. If you don't know, the numbers on there tell you what it is. The first 2 digits, the 20, is 20 millimeters diameter. The next one, the 16, means it's 1.6 millimeters thick. So it's 20 millimeters by 1.6. A CR 2032 will be 20 millimeters by 3.2 millimeters thickness, double the thickness of this. So you might find that in a typical digital watch these days. A capacity of 100 milliamp hours, and that's rated at 30K there, load. So that's 100 microamps load typically, 3 volts divided by 30K, 100 microamps. So it's lower than that, but you know, the capacity is not going to be hugely greater at any lower currents. We don't actually have any characteristic curves for ultra low currents here. We might be able to find it somewhere else, but you know, it's not quite shelf life, but it's getting there. Say a typical digital watch that might have, say, a 3-year battery life. I know you can get longer, but let's just say like a little digital watch that's just ticks over the seconds. That's all it does, you know, designed for ultra low power. How much current will that actually take at 3 years? Well, I've got my confuser here. Okay, 24, you follow along at home, 24 hours in a day times 365 days in a year, 8,760 times 3 is basically 26,280 hours. Divide 100 milliamp hours by that, and I'll just invert my register there, and we're looking at about 3.8 microamps there. So basically, for a 3-year battery life digital watch for one of these coin cells, you're looking at double the power consumption, 4 microamps, of the sharp memory LCD. Granted, this one is only this static consumption, but really the dynamic consumption, ticking over at once per second, say for a digital watch, it's not hugely, you know, larger than this. So it's, you know, it's basically, it's not going to be lower. This is still probably going to beat almost any, unless you engineer it really well, like you get in a watch with the custom ASICs and everything else, ultra low power solution. Any microcontroller with an LCD is going to take more than this. So let's actually just go in and have a look at some microcontrollers and confirm that. Because there were a lot of people out there that said, hey, just roll, I've done a do-it-yourself LCD tutorial, make your own LCD tutorial video, linked in at the end if you haven't seen it, where I could design a custom LCD, or I could use one. We could search DigiKey for a custom 7-segment LCD. I've got some here. You can get them on DigiKey. It's not a problem. Oh, all right, here we go. Out of the 1,500 LCDs, we want a 7-segment one. None of that 14-segment rubbish, as much as I love 14-segment displays. So let's say we want 5, 6, or 8. Yeah, they're all pretty large. I'm after quite a small solution. So anyway, you might be able to okay, that's a plasma. That's been miscategorized there on DigiKey. Oops, you know, you find errors like that occasionally. Anyway, these are quite large, but you could potentially either roll your own LCD. As I've shown in previous videos, it doesn't cost much at all. You could do it if you really wanted to do a segmented LCD, or you could find an off-the-shelf solution. But even these, like, you know, buying one off of these is not hugely cheap either. So what do you need for a microcontroller plus LCD solution? Well, first of all, you need an ultra low power microcontroller. There's quite a few of those on the market from many manufacturers, no worries. But you also need one that's got the LCD driver built in. In particular, for a 6-digit display, for example, you know, that's quite a large requirement in terms of number of segments to drive. So you're looking at a bigger chip, for example. So let's actually go into one of the traditional leaders in low power micros. They've got an app note here, this white paper thing, the TI MSP430. 100 nanoamps storage mode here, less than 500 nanoamps in standby, less than 1 microamp in RTC mode. We don't need a real-time clock here. We just need it to update the display, because the display is not static. You have to be still running the core at, say, the internal low power clock of 32 kilohertz, for example. There's no point running it any lower than that, really. 32 kilohertz is the go. Most micros for low power solutions will have built in 32 kilohertz you know, RC oscillators, so no problem. You don't need an external crystal. Timing requirements, there's no exacting timing requirements, so it's not a problem. But already we're pushing a microamp just running the RTC mode. Anyway, I know this is TI and it might be a bit biased, but they're trying to do an unbiased comparison with the PIC 24F micros over here, okay? So storage versus sleep mode. Now, storage mode is just where the microcontroller can retain data on the internal SRAM. It completely shuts down, the process is not running, but it can actually wake up with external interrupts and watchdog timers and other things like that. But it's basically just keeping data in SRAM going, and that's it. And you know, it can get as low as 100 nanoamps over here. The PIC is technically lower, but TI are claiming this is where you need to get into the nitty-gritty. So you can't just say go into a data sheet here and take like the banner spec up the top, you know, watchdog timer, deep sleep current. Like, you can't just take that at face value. You've got to know exactly what your requirements are, how you're going to wake the thing up. Can it wake from an internal watchdog timer? Can it wake from an external interrupt, or you know, some other thing like that? And that's what TI are trying to get to here. So there's lots of intricacies in low power design like this. So they're claiming that their low power mode 4 at 100 nanoamps, even though the PIC claims to be like 35 nanoamps, or with the RAM thing enabled to store some contents, it's 80 nanoamps. But with a brownout reset option, it actually takes more. So it's 60% plus higher, they're claiming over here. With a watchdog timer, they reckon the MSP430 is 600 nanoamps. Over here, 850 nanoamps. Anyway, what does all this have to do with LCD? Not much, because if you search this for LCD, they won't tell you anything. There's no matches whatsoever. So this is not driving an LCD. But basically, to drive an LCD, you've got to have the core of the processor, or at least the LCD module running. Then it's got charge pumps there that have to drive the bias voltages for the LCD. If you got the like a quarter bias LCD or something like that, like there's a few intricacies in there. I go into Microchip's nanowatt type ones for the ultra low power mode, extreme low power. Do they call it? No, they don't. Used to call it nanowatt, didn't they? Anyway, you go into the 8-bit microcontroller ones, and none of them, the 8-bit PICs, low power ones, none of them have LCD controllers built in. So right there, you're basically pushed in to the 16-bit PIC24F family, and only these higher end ones down here have LCD modules in them. Look, so you basically got to get one with a crypto engine and a USB and all sorts of things. And then if you go in and have a look at the bare minimum microchip one, LCD liquid crystal display, I can say that, controller, these are like big chips, like 64K SRAM. Not only are they expensive, but they're quite large as well. I think the smallest package is like a 44 or a 64 pin TQFP or QFN. It's like, man, gross overkill. With this thing, it takes 2 microamps guaranteed in static mode, plus you can drive it with a 3-cent microcontroller. It's going to be hard to beat this, if cost is no object, of course. But hey, Dave, there's other LCDs like this STM one, the 32LOX3. It's like it's got an LCD driver, 4x52, 8x48. No worries, right? But once again, these are like quite large, 20K of SRAM, 6K of embedded EEPROM, 32 pin is the minimum package, right? These are, I don't even have to look up the prices to know these aren't going to be hugely cheap. So you go into the product selector here, LQFP48 package, 32K of flash, 32, like, that's a significant part that has an LCD. Like, wow, like gross overkill for simply a power-up counter like this. It's sacrilege. But hey, if you look at the data sheet for this, okay, 400 nanoamps in stop mode, 16 wake-up lines, that's pretty good. 800 nano in stop mode plus RTC plus 8 kilobytes of SRAM retention, data backup, 88 microamps per megahertz in run mode. So you'd be using like stop mode for sure, assuming that the LCD controller works in stop mode. It may not. Search for that. Liquid crystal display. Drives up to 8 common terminals, 32 segments, late phase inversion to reduce power consumption and EMI. And bingo, the LCD controller can operate in stop mode. There you go. So it can be continuously updating. And then if you wanted to change it, like if you had a clock, for example, and a real-time clock running, you just interrupt that like once every second, and then you just update the display and then go back down into stop mode, which was what, 800 nanoamps or something like that. So in RTCC mode, real-time clock mode. Right, so you've got to go right down to the LCD controller down here, okay? And this is supply current at VDD 2 volts. Well, let's say it's supply current at 3 volts. Bingo, we're up to 3 microamps. And that is going to be, I think that's in addition, look at the asterisk down here, one LCD enabled with 3 volts, internal step up active, 1/8 duty, quarter bias, division array, all pixels active, no LCD connected. So with the extra little bit of capacitance on there, it depends how like often you update it and stuff like that. Like it's already more just this. And also it doesn't say anything about not including the residual consumption. So basically, you're looking in the order of really not going to get out of jail under 4 microamps. So double the consumption of this sharp memory LCD just to keep that solution of an LCD on a microcontroller running for this particular one here. Right, and I'm back to the pick here, and I'm trying to find, it's got deep sleep, brownout, reset, delta, and current, haven't found the LCD yet. By the way, I spoke about the low power RC oscillator, the 32 kilohertz one before. Here's the typical figure. This is over temperature range, doesn't vary a huge amount, but it could be anywhere from the min-max there. So as I said, if you want timing accuracy, you're going to have to use that external 32768 kilohertz watch crystal. But for an application like this, no wuckers. Look at all these performance curves. Going to town. Low power sleep, but give me LCD. Op-amp comparators. Oh, wow. How many? 353 page data sheet. How many errors in it? Guaranteed. Aha, DC characteristics. Here we go. LCD. Right, so that looks like a static from anywhere from 0.8 to 3 microamps. External, internal. Once again, that's just the LCD module current. LCD external, internal, 1/3 bias, delta LCD. Right, okay, so that's without the charge pump. With the charge pump here, it bumps it right up to 20 microamps. So if you've got a complex LCD, it needs all the charge pumps and stuff. Gonna come a gutser there, and it jumps up by almost an order of magnitude there. So, but once again, like 3 microamps, right? Max. Okay, the typical figure might be 0.8. So looks like the PIC's doing better than the STM micro in this particular case. But if you're designing for worst case parameters, which will change over temperature and stuff, then you've got to, which gives -40 to +85 here. That's only for the LCD, so then you've got to add on the extra. The PIC 24F plus a custom LCD could do the same current consumption as this. I'll give it that. But as I said at the start, you've got not only the cost of the custom LCD, but the cost of the micro as well. And it's a big micro because this is the smallest one we can get. I don't even want to know, the cost of that. It's not going to be a cheap micro. Not with that amount of memory. What? No. Damn it. Dev kit. Let's see what Grant Imahara tells us. Do they have it? There you go, $5. $4 in 100 of quantity. That sort of stuff. And it's a big ass micro. Okay, so let's have a quick look at the TI MSP430. There's nothing in the parametric search here for LCD. Aha, there it is, LCD there. So you've got to select, drill down into features, select that, and we can sort by price here. 95 cents, there you go, 60 pins, overkill, but okay, let's just run with this 48 pin jobby here, shall we? And once again, doesn't tell you anything in your high level specs. You've basically got to drill right to the end. At first browse over this, I'm just not having any luck finding a consumption for the LCD. It could be in there, but really, it's not that terrific. Okay, it might be lower cost than this if you get like a $1 LCD micro, for example, and you get your custom LCD, however much that costs to get made, and you amortize the cost over there. There's still like $1 each or something like that. It could be a cheaper solution, but it's bigger, more overkill than this little job, as I said, with a 3-cent micro. Right, so let's assume that we've got either of those solutions, and we're talking in the order of like 2 microamps standby consumption. Don't worry about when it powers up and all that sort of jazz. If we look at the circuitry here, we've got our product circuit. Let's say it's powered from USBs, powered from whatever. Anyway, we have to isolate our battery that we're going to use, or our supercap, or whatever our charge storage element is. We have to separate it from the rest of this, so that when you power down this, all the back circuitry in here, we're not going to get any back charge. So that's why you need to put that diode in there so it stops any reverse current. We're going to assume that we're going to get no leakage on that diode, like a 1N4148 or something will have like tens of nanoamps. It's not, it's not much. It's good enough for Australia. So then the battery, or the supercap, is only powering the micro and the LCD, and that's it. Total consumption, 2 microamps. So I just wanted to have a look at these funky new TDK Seracharge things. These are basically surface mount batteries, 1812 case size. You can pick and place them with your regular pick and place machine. And like really cool. I'm not actually sure how much these things cost, but unfortunately they've only got to up to 1,000 recharging cycles, so you'd have to go into the details of what happens, the longevity of them after that. Anyway, it's basically a multi-layer ceramic capacitor. You might think, okay, well, it's just a capacitor. Why has it got 1,000 charging cycles? Well, basically they're going to have ridiculously thin tolerances in there, and basically they're going to have a finite life, unlike a regular multi-layer ceramic capacitor, which wouldn't. This only goes to 1.6 volts. Wow, that's bugging naff all, isn't it? Sometimes like that'll be good enough to operate like a real-time clock chip. That's no good to operate our sharp memory LCD over here, which needs, it just says 3 volts. There's actually no, without the data sheet, we don't know what the lower limit of that is, let alone the micro. So you can actually stack them in series to get the 3.2 volts. Beauty. That could do the business, but you halve your capacity. And well, unfortunately, I think we're going to come a gutsy here. 100 microamp hours. You can't get any. That little tiny size is not magic, unfortunately. 100 microamp hours at 2 microamps, that's only 50 hours. Wah, 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 wah. Not good enough. So let's actually look at some supercapacitors, shall we? 1500, wow, they're a thing these days. When I was a boy, supercapacitors, geez, that was only a wet dream. Here we go, like the look of those. Nice surface mount ones from Seiko. 11 millifarads, 3.3 volts surface mount, 30,000 in stock, 68 cents. That's the business. Tape and reel packaging. Winner, winner, chicken dinner. Let's have a look. It's the thinnest and smallest chip-type electric double-layer capacitor. Unique ceramic packaging, superior air tightness is used. As a result, it offers leakage resistance. Cool. Backup power supply. It's exactly what we're looking at. 4.6 microamp hours. So that's really for short-term stuff. Once again, what do you expect in a package that small? I don't know. I'd tell him he's dreaming. Okay, so they're 11 millifarads, 80 millifarads. We're still not there. Look, these are getting decent size ones, but you know, 200 millifarads, we're still not there. It was only like a couple of hours discharge, and of course, you have to watch the thing with batteries and with supercaps as well. You have to look at the time over the minimum discharge. So what can your product, in this case the LCD, the sharp memory LCD, or your microcontroller plus LCD work down to, and still give you required contrast that you need to actually display your number when the power's off. We just don't know what that minimum limit is. It could be 2 volts, it could be 2.5. Don't know. And really what I want is an SMD, like a small solution. I'm going for a small LCD like this. Once again, your mileage may vary, but I'm going for an LCD something this small. Ideally, I want a tiny little source for it, right? So if you go up to a 1 farad capacitor, that's what a 1 farad supercap looks like. That's a 2.7 volts. That's an AVX job, really top quality. That's a 10 farad jobby, and that's a 50 farad 2.7 volts. So these things are just like enormous. All right, so let's calculate how long a supercap will last. In this case, I'll take this monster example, 50 farad supercap. Okay, we'll use an online calculator, makes it easy. There's the formulas down there. Have I done a tutorial on time constant formulas? So we're looking at 3 volts, and of course we need a minimum voltage that we're going to discharge to. Let's say 2 volts. Our capacitor size, 50 farads. We don't worry about the ESR, doesn't matter with this sort of low current, and a maximum of 2 microamps. And bingo, it calculates out that, you put it on the confuser, calculates, let's round it to 7,000 hours. It might be okay for my application, but look at the size of the thing. Anything smaller, 1 farad jobby, it's 50 times less. Forget it. So supercaps aren't any good at all if you need small size and long discharge, even at a tiny 2 microamps, which is about as low as it gets. Really, you can engineer slightly lower, but you're not going to get an order of magnitude lower, really. But even then, they still aren't going to do the business. They might if you've got heaps of space available. Okay, no wuckers. You can't beat battery chemistry. The CR 2016 battery over here. Oh, I love the high energy density chemistry. 100 milliamp hours, and that is to 2 volts. Okay, so exactly the same from 3 volts to 2 volts discharge. It's a much smaller volume than this. 100 milliamp hours divided by our 2 microamps. That's 50,000 hours. No comparison between a coin cell battery and you can even use like a smaller one. I'm just using 2016 as an example. Okay, or you can get, you know, solder ones directly onto the board, the tabs and stuff like that. If you are okay with the product actually being like single use, but in my particular case, it'd be nice if it like recharged. If it did it. Look, this is why I'm trying to avoid a battery solution altogether, a supercap solution altogether, and it's why I looked at originally the e-ink display, because it takes all this out of the equation. And if we could simply get an e-ink display like this size with the 7 segments, you don't need any backup solution at all, and it does exactly what I want, which is just leave the static image on the display. There's just no contest between the 2 solutions. You'd go e-ink every time if you could get it, because there's just no contest. Dicking around with supercaps and batteries and discharge curves and times and recharging schemes and back diode to prevent this and that. Nah, like, come on. Anyway, yeah, poor old supercaps, they just don't cut it. And even these like little cool technology of these little micro SMD batteries, they just don't cut it either, only for very short cycle times for preventing stuff when they go down and things like that. So there you go. I've waffled on enough already, long enough, more than long enough, and there you go. I wish I could get an e-ink. I'm still going to look at getting e-ink solutions, still working on it. I just people wanted to know about this stuff, so hope you found that interesting. If you did, please give it a big thumbs up. As always, discuss down below. Catch you next time.